So good morning. We are now going to answer chap exercise 5.1. This is from chapter 5, applying Newton's laws of motion. So this is section 5.1, using the Newton's law of motion, Newton's first law of motions, particles in equilibrium. So we are using here the University of Physics with Modern Physics, the 15th edition by Young and Freedman. So by the way, I am Prudence Peace Bustamante. I'm a physics instructor of the uh, Surigao del Norte State University here in the Philippines. So let's proceed to the problem. So the problem states that two two to 25.0 Newton weights are suspended at the opposite ends of the rope that passes over a light frictionless pulley. The pulley is attached to a chain from the ceiling. What is the tension in the rope? What is the tension in the chain? Okay, since this problem is an equilibrium problem, therefore we're going to start to use the Newton's first law of motion. Okay, so the first thing you do in dealing with uh, apply Newton's law problem or applying Newton's laws of motion problems is draw always the free body diagram. Okay, so let's draw the setup. So we have here a ceiling. Okay, this is, so for example, we have a ceiling here, and the problem said that it has the pulley. You have a chain here. You have a chain, and we have a pulley here, and the two units are suspended opposite using a rope. Okay, we have here uh, the weight one, and we have here in the other side. Okay, assuming this is a balance weight two. Okay, so what can we say? This is a rope. So we have the tension on the rope. Okay, we have the tension on the rope. So this both tension here are equal, and we have here the tension on the ceiling. Okay. This is this is the ceiling. Okay. So this is the setup of our problem. Okay. So the pulley is light and frictionless. So therefore, because it's frictionless, the tension here are equal, and also uh, this pulley has a negligible weight, or it has a negligible mass. Okay, so let's draw the free body diagram. Okay, let's draw the free body diagram. Okay, the free body diagram of uh, the the weight one first and weight two. Okay, the the weight one, which is equal to 25 Newton. Okay, for the weight one, so we can see here that if you are the object, this is a y and x component. I mean x component. Okay, so the forces acting on you, if you are the weight one, you have here the tension on the rope upward, and downward if you have the tension on the weight one. Okay, wait. So what else? Free body diagram of weight two. So the weight two here, the same setup. Here we have the tension of the rope, and we have the weight two here. This is Ry. Okay, this is an equilibrium. So we're going to use the Newton's first law of motion here. Summation of all the forces along y. This is equal to, what are the forces? So we have upward, the tension R, plus the negative of the weight one because it is downward. Since this is an Newton's first law. This is an equilibrium problem. Then we're gonna use the Newton's first law. This is equal to 0. So if you recall, the Newton's first law states that uh, in equation, it's like this. Okay, the net force is equal to 0, then the object is in equilibrium. Okay, or in components and y components is equal to 0. It has if there is a z component, then this is equal to 0. Okay. How about also the same summation of Fy is equal to the tension of R plus the negative of weight 2 is equal to 0. How about the free body diagram of the pulley? We have the free body diagram of the pulley. Okay. To draw the free diagram of the pulley, it looks like this. If, uh, so we have the tension on the ceiling. Okay. Tension on the ceiling. And if we can also put it like this. We have the tension, first tension, and we have here tension of R. But I would like to put this like this. Okay, tension of the ceiling, and here the tension, which is equal to 2 times the tension on the rope, because there are two weights here hanging. Okay, so so if this is a combined tension. Okay, if you are the pulley, so you are pulled upward by. Okay, maybe we put this one here like this. Okay, we are gonna put this one like this. Tension on R weight 1. You also have downward tension equal in magnitude. Uh, tension plus tension of R. Okay, that one. There are two tensions here downward. Okay, so but if we combine this like tension T is just 2 times the tension R, or just gonna add this one. If you're the pulley, you are pulled by those two weights. There are tensions pulling on you too, and there are tensions pulling you upward. So the question is, what is the tension on the rope? What is the tension on the rope? Okay. So we can, by the way, let's continue this first. Summation of all the forces along Y. By this equation, I'm gonna use this free body diagram. For the pulley, is this equal to the tension on the ceiling plus the negative of the 2 times the tension on the rope. This is equal to 0. Okay. So, so to answer letter A, okay, so let's answer letter A. We can use this equation actually. Here, the tension R is equal to weight 1. Okay. We have this equation 1, or we can also use this one. So letter A, what is the tension on the rope? So the tension on the rope, since this one is equal, they have the same magnitude, so the tension on the rope is just equal to the weight 1, which is given, which is 25.0 Newton. So that's our answer for letter A. How about letter B? Okay. What is the tension on the ceiling? Or the chain? What is the tension in the chain? To answer this, so we can generate our second equation from the pulley equation. This is equation 3. Tension on the ceiling is equal to, so we're gonna transfer this one to the other side, 2 times the tension on the rope. Okay, so therefore this is our equation 3. Okay, from equation 3, okay, because this is our equation 2. From equation 3, we can get that the tension on the ceiling is equal to 2 times the tension on the rope, which is we know that is 25 Newton, 2 times 25.0 Newton. So this is equal to, okay, which is equal to 50.0 Newton. So that's the tension on the ceiling. Okay, so this ends our video for this ends our lesson for exercise 5.1.